Have you ever wondered if what you see, touch, and feel is truly real? What if I told you that scientists have proven that nothing is really as it seems? The central question about the nature of reality is one of the deepest we can explore. Is there a physical reality independent of our perceptions? Some scientists and philosophers argue that time and space might just be constructs of human perception, tools that our brain uses to interpret the world around us. This perspective suggests that what we perceive as real may be an illusion, a subjective interpretation of a much more complex and mysterious universe. Consider the idea that what we see and feel is only a limited representation of a vast and inaccessible reality. Our perceptions are shaped by our senses and brain, which filter and interpret information in specific ways. This leads us to question, to what extent can we trust what we perceive? If our senses can deceive us, how do we know if what we see is truly the truth? These questions are not just philosophical, they have direct implications for science, which seeks to understand the fundamental nature of the universe. Modern science is increasingly inclined to explore these concepts, suggesting that our understanding of time, space, and matter might be much more fluid and interconnected than we imagined. This investigation leads us to consider the perspective of neuroscience, which studies how our brains construct reality from sensory inputs. Neuroscience suggests that our brains not only receive information from the world around us but also construct a version of reality based on these sensory inputs. This model of the world is created from electrical signals that our senses send to the brain, which then interprets these signals to form a coherent image of the environment. However, this process is not perfect and can be easily distorted, as demonstrated by optical illusions and other perceptual phenomena. For example, visual illusions show how our brains can be tricked, making us see things that do not exist or perceive characteristics that are not present. These perception errors reveal the limitations of our sensory system and make us question the accuracy of our mental model of reality. If our brain can be so easily fooled by simple tricks of light and shadow, what does this say about the trust we place in our everyday perception? This neuroscientific perspective leads us to a deeper understanding that the reality we perceive might be a mental construction, an interpretation of what our senses capture. This challenges the idea of an objective and independent reality, suggesting that what we consider real is actually a subjective and potentially fallible version of the universe. Philosophy has long debated the nature of reality and our ability to know it. Philosophers like Plato and Descartes questioned the veracity of sensory perceptions, suggesting that what we perceive might not be the true reality. Plato, with his famous allegory of the cave, proposed that what we see are merely shadows of a deeper reality. Descartes, on the other hand, questioned his own existence, concluding that the only certainty was that he was thinking, summarized in his maxim, "I think, therefore I am." Philosophy proposes that reality is objective and exists independently of our perceptions. However, it also acknowledges that our sensory perceptions are fallible and prone to error. This raises the question, how can we know the true nature of reality if our perceptions are imperfect? Kant argued that we can never know the thing in itself, only its appearances, filtered through our cognitive structures. This means that our understanding of the universe is ultimately limited by the capacities of our mind. These philosophical debates continue to influence modern science, especially when we consider theories that challenge the classical view of the universe. Quantum theory, for example, introduces fundamental uncertainties in the measurement of subatomic particles, suggesting that reality might be intrinsically indeterminate. Developed in the 1920s and 1930s, quantum theory revolutionized our understanding of the universe by introducing fundamental uncertainties in the measurement of subatomic particles. One of the pillars of this theory is Heisenberg's uncertainty principle, which states that we cannot know both the position and momentum of a particle with absolute precision simultaneously. This intrinsic indeterminacy challenges the classical view of a deterministic universe, where everything can be predicted if we have enough information. Moreover, quantum mechanics suggests that particles can exist in multiple states simultaneously until they are observed, a phenomenon known as superposition. Only when a measurement is made does the particle choose a specific state, collapsing the superposition. This strange behavior of quantum particles led to the famous Copenhagen interpretation, which posits that physical reality depends on the observations made by an observer. In other words, reality might not exist definitively until it is measured. These revolutionary ideas of quantum theory not only challenge classical physics but also raise profound questions about the very nature of reality. If observation can influence the state of a particle, what does this say about the universe on a large scale? Quantum theory paves the way for discussions about hidden variables and the possible existence of unknown factors that might determine the seemingly random behavior of quantum particles. The idea of hidden variables emerged as an attempt to explain the apparently random behavior of quantum particles. According to this theory, there are unknown factors that determine the behavior of particles, but that have not yet been discovered or understood by science. If these hidden variables exist, they could provide a more complete and deterministic explanation of the universe, aligning quantum mechanics with the classical view of physics. One of the main proponents of the hidden variables theory was Albert Einstein, who famously said, "God does not play dice with the universe." Einstein believed that quantum mechanics was incomplete and that a more fundamental theory, with hidden variables, could explain the inherent uncertainty and probability of quantum theory. However, so far, no concrete evidence has been found to support the existence of these hidden variables, and quantum mechanics remains the best description we have for the behavior of subatomic particles. The hidden variables theory remains a topic of intense debate and investigation. Experiments like Bell's test have shown that if hidden variables exist, they must obey very specific rules that differ radically from classical expectations. These tests have demonstrated that quantum mechanics, with its indeterminacy and probability, offers a more accurate description of subatomic phenomena than any tested hidden variables theory. To better understand this quantum strangeness, let's explore Wheeler's interferometer experiment, which highlights how quantum particles can know how to behave. Wheeler's interferometer experiment, also known as Wheeler's delayed choice experiment, is one of the most intriguing in quantum physics. This experiment explores how quantum particles, like photons, seem to know whether to behave as waves or particles, depending on the experimental setup. The central idea is that the decision to measure a particle as a wave or a particle can be made after it has already passed through the interferometer, suggesting that quantum reality is determined at the moment of observation. In the experiment, a photon is sent through an interferometer that can be configured to measure the particle as a wave, producing an interference pattern, or as a particle, not producing an interference pattern. The surprising thing is that if the choice to measure as a wave or particle is made after the photon has already passed through the interferometer, the photon still chooses the correct behavior according to the final configuration. This suggests that quantum reality is not determined until the measurement is made, highlighting the deeply mysterious nature of quantum mechanics. This experiment challenges our intuitive understanding of cause and effect, suggesting that events at the quantum level do not follow classical logic. The implication is that reality can be influenced retroactively by how we choose to measure particles, an idea that seems almost magical. These results have led many scientists to reconsider the nature of time, causality, and reality itself. This quantum strangeness leads us to investigate the relationship between quantum mechanics and consciousness, where theories suggest that consciousness might emerge from quantum processes. The relationship between quantum mechanics and consciousness is a field of study that challenges our conventional understanding of mind and matter. One of the most intriguing theories suggests that human consciousness might emerge from quantum processes in the brain. Physicist Roger Penrose, along with anesthetist Stuart Hameroff, proposed the theory of orchestrated objective reduction, orchestra-OR, which suggests that consciousness is not algorithmic but rather the result of quantum processes in the microtubules of neural cells. According to this theory, microtubules, which are structural components of neural cells, could function as natural quantum computers. The quantum interactions in these microtubules could generate the phenomena of consciousness, linking fundamental physics to the emergent behavior of the mind. This idea is radical because it implies that consciousness is rooted in the fundamental properties of matter and energy, and is not merely a byproduct of classical neuronal interactions. The idea that consciousness might be linked to quantum processes suggests that the human mind could be deeply and intrinsically connected to the quantum universe. This raises fascinating questions about the nature of perception, reality, and existence itself. If consciousness emerges from quantum processes, then the line between mind and matter becomes much more tenuous, suggesting a new view of reality where consciousness plays a central role. This leads us to consider even more expansive theories, such as the multiverse and the holographic hypothesis, which offer new perspectives on the nature of reality. Theories of the multiverse and the holographic reality propose that our reality might be just a small part of a much vaster and more complex universe. The multiverse theory suggests that there are multiple parallel universes, each with its own physical laws and initial conditions. These ideas arise from quantum physics and cosmology, where certain interpretations and solutions to equations indicate the possibility of multiple universes. If true, the multiverse would imply that our own existence is just one among infinite possibilities, each unfolding in its own reality. In cosmology, the idea of the multiverse is supported by the concept of eternal inflation. Inflation is the rapid expansion that the universe experienced a moment after the Big Bang. According to this theory, some regions of space continue to inflate while others stop, creating bubbles of the universe that are independent of each other. Each of these bubbles could be a universe with its own physical properties. This means that what we observe as our universe is just one of these bubbles, and there are many others, potentially infinite, beyond ours. String theory also suggests the existence of a multiverse. In string theory, fundamental particles are actually tiny vibrating strings that exist in multiple dimensions. These extra dimensions can be compactified in various ways, each corresponding to a different universe. M-theory, an extension of string theory, suggests that there are 11 dimensions and that our three-dimensional universe might be just a brain floating in a higher dimensional space. This view opens the possibility that many other universes exist with different properties, completely separate from ours. The multiverse theory raises profound questions about the nature of reality and our position in the cosmos. If there are infinite universes, this means there are infinite versions of ourselves living different lives in parallel universes. Every choice we make could generate a new universe, creating an infinite tapestry of possibilities. These ideas not only challenge our scientific understanding but also have profound philosophical implications, forcing us to reconsider the uniqueness of our existence and the nature of free will. The holographic hypothesis, on the other hand, suggests that the three-dimensional universe we live in might be a projection of information encoded on a two-dimensional surface. Leonard Susskind and Gerard T. Hooft were pioneers of this idea, which is based on discoveries about the entropy of black holes. If the information that makes up our universe can be stored on a two-dimensional surface, this implies that what we perceive as three-dimensional reality is actually an emergent illusion from a more fundamental and simpler structure. The holographic hypothesis has profound implications for our understanding of space, time, and reality. If the universe is indeed a holographic projection, this means that our three-dimensional perceptions are an emergent illusion from a more fundamental and simpler reality. This also implies that the physical laws that govern our universe might be described by a theory operating in a lower dimension. This idea has been explored in various areas of theoretical physics, including string theory and quantum gravity. Experiments in particle physics and cosmology continue to seek evidence that might confirm or refute the holographic hypothesis. Some scientists are examining the cosmic microwave background, the remnant radiation from the Big Bang, looking for signatures that could support the idea of a holographic universe. Additionally, research in quantum gravity and string theory is exploring how the holographic hypothesis might resolve paradoxes and unify our physical theories. Considering these ideas, we begin to understand that what we call reality might be just one facet of a vaster and stranger cosmos. Following this line of reasoning, we consider visual illusions, which are powerful demonstrations of how our brains can be easily deceived, highlighting the fallibility of sensory perceptions and making us question the nature of the reality we perceive. These illusions occur when there is a mismatch between physical reality and the interpretation our brain makes of the sensory information received. They show us that our perception of the world is not a perfect representation of reality but a construction created by our brains. A classic example of a visual illusion is the Muller-Lyer illusion, where two lines of equal length appear to be of different lengths due to the arrows at their ends pointing inward or outward. Our brain interprets these lines differently based on contextual clues and past experiences, leading us to perceive different lengths. This type of illusion reveals how our brain uses shortcuts to quickly interpret the environment, but these shortcuts might not always be accurate. Another fascinating illusion is the Ames room perspective illusion, where a seemingly normal room is designed so that objects and people appear to grow or shrink as they move within it. This illusion takes advantage of our expectation that parallel lines and right angles define the space around us. By manipulating these expectations, the Ames room illusion demonstrates how our spatial perception can be easily distorted. These visual illusions are not just interesting curiosities, they have profound implications for science and philosophy. They remind us that our perception of the world is an active construction of the brain, and that this construction can be easily manipulated. This raises questions about the extent to which we can trust our perceptions to understand reality. These reflections lead us to another theory, the integrated information theory. Proposed by neuroscientist Giulio Tononi, it offers an innovative approach to understanding consciousness. According to the integrated information theory, consciousness is an emergent property of systems that possess a high degree of information integration. In other words, consciousness arises when information within a system is highly interconnected and interdependent, forming a unified whole that is greater than the sum of its parts. The integrated information theory suggests that any system that processes information in an integrated manner might possess some degree of consciousness. This implies that consciousness is not exclusive to biological organisms but might be present in any sufficiently complex system, including machines and even non-biological structures. This perspective challenges the traditional view of consciousness as an exclusively human phenomenon and opens new possibilities for exploring the mind and perception. Applying the integrated information theory to the study of the human brain has revealed fascinating insights into the nature of consciousness. Research shows that different states of consciousness, such as sleep, wakefulness, and altered states, correspond to different levels of information integration in the brain. The integrated information theory provides a theoretical framework for understanding these states, suggesting that the amount of integrated information correlates with the intensity and quality of the conscious experience. In addition to its application in neuroscience, the integrated information theory also has implications for the philosophy of mind and our understanding of reality. If consciousness is an emergent property of integrated information, then the universe itself might be seen as a vast system of interconnected information. This leads us to consider the possibility that consciousness and perception are fundamental to the structure of the cosmos, connecting the human mind to the complexity of the universe in profound and unexpected ways. Exploring these theories and discoveries leads us to deeply question our understanding of reality. From visual illusions that deceive our senses to quantum mechanics that challenge our classical view of the universe, we realize that what we consider real might be a much more complex and mysterious construction. These ideas are not just abstract theories, they have the potential to transform our view of the world and ourselves. They show us that reality is much more than what we perceive at first glance and that there is still much to discover about the true nature of the universe. Continuing to explore these frontiers of knowledge is essential for expanding our understanding and opening new possibilities for science and philosophy. If you enjoyed this journey into the unknown and want to continue exploring the mysteries of the universe, subscribe to the channel and activate notifications. Join us for more scientific adventures and keep expanding your mind with the wonders of the cosmos. See you next time.